Hello, this is Jack Jackson. In this video, we're going to be talking about Ptolemy and Greek astronomy a little bit. And we may come back and talk about this figure here in just a little bit. But let's first talk about astronomy and mathematics. Throughout history, the apparent movement of the sun, moon, stars, and planets in the sky has fascinated human beings. And the study of astronomy has led to some significant mathematics, and mathematics has been used to further the study of astronomy. The earliest people had supernatural explanations. For example, the Greeks thought the god Apollo drove his chariot of the sun across the sky, and his sister Artemis drove her chariot of the moon across the sky. As time went on, uh, scientists tried to describe a little bit more what was happening in terms of explaining what they could see. And the two main models that came to mind are geocentric versus a heliocentric model. In a geocentric model, Earth is the center of the universe, and everything kind of goes around the Earth. Heliocentric is the sun is the center of the solar system. Of course, now we have enough evidence that we know for sure that the heliocentric model is correct. But the geocentric model is not an unreasonable model given the um, inputs that folks had at the time. When you're talking about making observations by the naked eye, it looks like you're stationary on Earth and things are revolving around the Earth. It was pretty well known that the Earth was actually not flat, although that might be the first appearance. But there were enough observations that were made to know that the Earth was more or less spherical in shape, and we know that some of the Greeks, Eratosthenes, for example, being the first one, was able to measure the size of the Earth, at least give some approximation of that. But still, this idea that we have the Earth here, and it looks like the sun, and is rising in the east and going down in the west, and maybe working its way around the Earth and then back up again. And the moon did something similar, and the stars uh, transverse the sky in some of a circular pattern as well. And so we got some interesting things there. So it's very interesting. Of course, the sun, the cycle of night and day, and then the cycle of seasons, and then the cycles of the moon as well, were big things that affected life, everyday life, and still, of course, do to this day. Now, one of the things that became interesting is that the idea of the seasons, and folks pretty quickly noticed that there was a seasonal pattern of one what we now call a year, where the sun, where we know now that the Earth is going around the sun, so starting at one place relative to the sun and revolving one whole full time around the sun back to where it starts, it's one solar year. Unfortunately, that doesn't work out to exactly the same as a day. A day, of course, being the amount of time that it takes the Earth to spin on its axis. Of course, the geocentric model wouldn't have had the Earth spinning on its axis, but rather um, the sun going and the moon and the stars going around the Earth. But anyway, it doesn't turn out that it's exact number of days. It's just a little bit under 365 and a quarter days for a year. So with that not matching up exactly the number of days, that little extra quarter of a day makes for an interesting thing when you're making up calendars. And so one type of calendar would be based on the sun, so that you look at the transpiring of the years going by. Another calendar could be based on a lunar calendar, where we have a month, which is an actual month. Lunar month is the amount of time it takes for the moon to make one orbit around the Earth. And in that case, they were correct that the moon is actually going around the Earth. And that, again, is not a whole number of days. It's approximately 29 and a half days. So, and unfortunately, a solar year is not a multiple of a lunar year. It's more than 12 months. Okay, a little bit more. And so if you make a calendar that's based on the moon, it's not going to line up with a solar calendar. If you make a calendar based on the sun, it won't necessarily line up with the moon. And our solution nowadays is to pretty much ignore the moon, is what's the calendar that we use now is a solar calendar. But some folks still use a lunar calendar um, as well. Now, when we start looking at the sky, the thing that's going to capture people's attention, and these are things that you can observe with the naked eye, are not only the sun and the moon making this apparent trek, there's some variations of what's going on there. For example, the sun doesn't rise in the exact same place every time. It changes throughout the seasons. Okay, and some of the same things happen for the moon. The moon is extremely interesting because it does not stay an apparent circle the entire time. It goes through the phases of the moon. That's something that's interesting, and so that requires some sort of explanation as we investigate that. Now, if you live in the northern hemisphere, there's Polaris, the North Star, which is apparently fixed in position with all of the other stars rotating around it. And then you come across the planets. And the planets were some of the most interesting things because the planets didn't behave like the stars. If to the naked eye, they look more or less like stars. They're little lights in the sky. Definitely not the same as the sun. The sun is so much bigger, and the moon are so much bigger. But these little, it's kind of like more like the stars, at least to the naked eye. But unlike the the stars and the sun and moon, it has a completely different kind of path. And in fact, it basically, throughout the time seems to be going across the sky, kind of like the sun or the stars do. But then it sometimes reverses direction. It has something called retrograde motion. Oh, that's really interesting. So they basically started naming these guys the wanderers, what the word planet means, the wanderers. So they're wandering around, sort of going in their own path, somewhat in a regular path, but very different than the stars. So something happens there. Very interesting. So the planets that they could see were Mercury, Venus, Mars, Jupiter, and Saturn. There were 5 planets. Of course, they're not really thinking of Earth as a planet at this point. So there are 5 planets that they could see. And there are also 5 platonic solids. So folks like Plato would have thought there must be some kind of interesting connection there. The platonic solids are the regular polyhedra. And so they were considered sort of really sort of examples of sort of really idealized figures, and since there are 5 of those 5 planets, maybe they had something to do with each other. They also considered a sphere sort of the uh, the ultimate shape, and so they used spheres to try to explain what was going on. A lot of this stuff goes back to Pythagoras, although uh, the heliocentric theory and the geocentric theory were both in play in the Greek world. At least as far back as some of the Pythagoreans, there were examples of a heliocentric model. But pretty soon, eventually, or not pretty soon, but eventually, the geocentric model became sort of the dominant one. Now, another thing that's interesting is the whereas the Greeks used a number system that was mostly grouped in, well, it was grouped in tens, not exactly a base 10, certainly not a base 10 place value system like we have now, but a base 10 system in the sense of grouping of tens. But for astronomy, they typically use a sexagesimal system, which of course indicates that they may have started by learning a lot of their astronomy from the Babylonians. So a lot of the early astronomy was Babylonian, and some of that tradition then went over to the Greeks as well. And so a lot of the calculations and the measurements and so forth were done with a Babylonian type of system, not cuneiform writing necessarily, but this sexagesimal idea. Okay, so the main point here is the thing that people could actually see if they would just look up and pay attention and record it are these fascinating things that are going on in the sky, and how do we explain these movements? And when you start to try to explain them scientifically and mathematically, that generates some and stimulates some interest in mathematics to make these explanations happen. Some kind of geometry that's going on here is going to be developed to help try to solve these problems or these challenges of explaining what's going on in astronomy. So astronomy really helped spur along the growth of mathematics, and of course mathematics then helped spur along the science of astronomy. Now, in fact, uh, ancient astronomers and mathematicians were often the same thing. In fact, astronomers were probably all mathematicians, and some mathematicians were astronomers. And one of the most influential, I'd say maybe the most influential for many, many years, was a mathematician named Claudius Ptolemy. He lived in the late first and early second century, the Common Era. So now we've finally gone past the life of Jesus here and gone into the Common Era. Uh, he was born in 85 CE and died at 165 CE. And guess where he lived? Yep, Alexandria, Egypt, the center of mathematical thought for many years there. According to the MacTutor History of Mathematics, there has been some controversy among mathematicians concerning his abilities. Um, there's a lot of evidence that he was a very outstanding mathematician. He definitely, most undoubtedly, was very influential. But there's some historians that have claimed that his abilities were a little weaker, and that he was mostly an expositor of other folks' works. And a few have even claimed he was unethical, that he actually collected some data that he knew didn't jive with his models, didn't agree with his models, and so then he actually just basically lied about the data. So there's some controversy. I'm not going to take any sides here, but you can read a little bit more about that in MacTutor's article on that, and then branch out to some other sources if you're interested. But undoubtedly, he was extremely influential, the most influential astronomer and geographer of his time. I just want to take a second to talk about his name, Claudius Ptolemy. Claudius is a Roman name, Ptolemy is a Greek name. Ptolemy was the name of Alexander's successor who ruled the portion of the former Alexandrian Empire that contained Egypt, and the rulers in Egypt were named Ptolemy. Okay. However, Claudius Ptolemy was not such a ruler, and we have no idea of his connection to that ruling family, if there is any. So don't confuse him with the rulers of Egypt, the Ptolemies that ruled Egypt. Since his Roman name Claudius indicates that he was probably a Roman citizen, so he was someone that was a intellectual scholar who lived and worked in Egypt, in Alexandria, there in the library, in the museum, with the other scholars of the time. He enjoyed some status as a Roman citizen. By the way, notice by this time the Roman Empire has control of uh, of Egypt. Okay. Now let's talk a little bit about what he did. His most important work is now known as the Almogist. It was originally translates to English as the mathematical compilation or the mathematical collection. And then later on, it was called the greatest compilation to distinguish it from some other collections. The Arabs called it Almagesti, and that got translated back into English as the Almagist or Almagist. So, and that's the way it's known today as the Almagist. So, the Almagist, in a lot of ways, was kind of like it kind of was to astronomy what the elements was to geometry. It had 13 books. It, like the elements, it compiled earlier work, in this case earlier astronomical work, going back probably to um, some work that was inherited or learned from Mesopotamian mathematics, and then and mathematics and astronomers into the Greek world as well that came before this. Many generations of work were put together, and then it was also expanded upon considerably. And in this work, it gives a geocentric model of the universe. Now, again, they didn't have the examples they didn't have the instruments that we have today to measure the universe, and so I mean a geocentric model is reasonable given what they had to work with, but it had to be fairly complicated to explain things like, for example, the retrograde motion of the planets. And so they came with a very detailed model that fits the data pretty well, and it makes use of spherical orbits with epicycles. So here's a couple pictures. This is from Encyclopedia Britannica, where it shows the Earth here, um, and some places where the Earth wasn't quite at the center here, but it has some circular orbits here with the circles going around inside of that. So if you kind of look at the picture here, if you take a point here that's going around the circle here, and then going around, that whole circle is going around the big circle. Think of the teacup ride at Disneyland, right? And so this is going around like this, and look at where the planet's going. It's going around this way, makes this kind of a loop, makes these loops. So if you look at it, basically it's kind of going around the big circle, say in the positive direction here, but every now and then it stops going that way and sort of turns around and runs backward for a little bit. There's your retrograde motion. And they felt like this was the path of the planets. They they needed to do this because they were operating on some postulates that they felt that the circle was the simplest form, that the path should be around circles, and the postulate that the Earth was the center. One of the arguments they used that the Earth was the center is, well, if the Earth was moving around, wouldn't the clouds uh, be apparently moving in the opposite direction really fast, because they wouldn't go with the Earth because they're not attached to the Earth? And we know we can explain that today, why they made that erroneous uh, assumptions, why these postulates were incorrect. But nevertheless, that's what they used. So this model actually fit the data pretty well, and it held dominance for nearly 1,500 years. It wasn't until after the work of Copernicus, 1,500 years later, and even really much after him, before a heliocentric model became accepted. And so this Almogist actually just really dominated the field of astronomy for a long time. Now, some of the things that were in there, the mathematics that were needed to explain all this, includes the use of a function called the chord function. It's kind of related to a sine function. It's a trigonometric function. And one of the things that Ptolemy collected and made, whether he made them himself or perhaps there's a good chance he had a bunch of calculators, people who would do calculations to help make values of this function. And they made huge tables in increments of a half a degree, and were able to find this chord function for values of this chord function for several angles. Now, there's no evidence that he actually thought of this as a function in our modern day sense, but he was really close to this idea, so where he had these ideas of inputting the angles and outputting the values of this chord function. And using this chord function, he could, just like we can use sines and cosines today, he was able to do some trigonometry. And for one thing, he was able to solve plane triangles using the techniques that are equivalent to the law of cosines and the law of sines. We know now today that we can use the law of sines and law of cosines to solve any triangle if we're given basically three pieces of information about sides and angles. We can solve for the other pieces, or at least give the possibilities for the other pieces when there's more than one. And he could do the same thing using the chord function. He was able to also do a lot of work with spherical triangles because really this is a 2D picture here, but he's really thinking of all this in terms of 3 dimensions. So he was doing a lot of work with spherical geometry basically and working with spherical uh, triangles and he was able to solve those as well. Again, making use of this chord function. He was able to get approximation of pi. He used 3 and 17/120ths, which works out to be about 3.14166. They had a method of extracting square roots, and there are tables of square roots. Apparently, Ptolemy's writings don't give the algorithm, but some later algorithms do explain it, and that algorithm is similar to was probably what Claudius Ptolemy and his um, calculators probably used. For example, they approximated square root of 3 as 1.73205. He's known for a theorem in geometry called Ptolemy's theorem. In a cyclic quadrilateral A, B, C, D, so we have a quadrilateral here, okay? And so the vertices are A, B, C, and D going around there. And there is a circle which goes through all four of those. Not all quadrilaterals will that work, but there are certain ones that will work. And he said for this, the sum of the products of the lengths of two pairs of opposite sides equals the product of the lengths of the diagonals. So in other words, if you take the distance from A to B times the distance from C to D, multiply that, then multiply the other two sides, the distance, the lengths B to C times the distance from D back to A, multiply those two, add those, you get the same thing if you just multiply the lengths of the two diagonals. It's kind of a generalization of the Pythagorean theorem. If the quadrilateral is a rectangle, I'll let you think about this a little bit. I want you to work it out that this is exactly the Pythagorean theorem. Now, what kind of things did he have? Of course, we talked about the Almogist, which is probably his most influential work. But he also, there were some trigonometric tables, these chord tables in the Almagest, but there was also a book apparently called Handy Tables, which was basically just trigonometric tables. There was a book called Planetary Hypothesis, and it replaces some of the geometric theories and proofs of his method with mechanical ones, and making the material more accessible to less mathematically advanced readers. So this is sort of a more popular science type of a book compared to his more theoretical science thing. He wrote a book on astrology, which he would have thought as a companion to his Almagest, because one explains how the system operates, and astrology would say, well, why does it operate this way? Um, there's another work here, Analemma. So he found angles for a sundial, among other things. There's one called Planispherium, where he talks about stereographic projection of a sphere on a plane, and that would be useful for making maps that are from a globe and putting it onto a flat map. And one of the other things that he was very famous for was a book on geography. It was actually 8 books. And in that, he gives a map of the full known world with latitude and longitude coordinates. It was pretty good in this. This is sort of a picture of his map. And it was pretty good for this part right here in the Roman Empire around the Mediterranean Sea was pretty good. As you get to the farther reaches of the Roman Empire, it's a little less good. Like, for example, here along the coast of Africa, not really sure what's going on down here. You notice when you get over here to India, there's some definite uh, problems with the Indian subcontinent here. But it's pretty good in this area here. And this became one of the first main big attempts at trying to map out what was the known world to him at the time in some real detail and give it in terms of some kind of coordinates as well. He also did a book on optics. So Ptolemy was Very influential mathematician and especially astronomer and geographer as well.